What is greener or environmentally preferable? A ceramic mug or a paper cup? The answer is not trivial, as the systems under assessment can easily trigger a cascade of processes that are highly interconnected and are dispersed across the global economy. Hello, my name is Stefano Cucuracchi. I research and teach in industrial ecology at Leiden University at the Institute of Environmental Sciences, CML. My area of expertise is industrial ecology. And today, I will be talking about one of the key methods of the field, life cycle assessment, or in short, LCA. We started with mugs and cups, but try now to think of supporting decision makers to assess the environmental performance of alternative options. Try now to imagine undoubtedly more complex systems than mugs and cups. Think, for instance, of comparing alternative designs for power plants, or alternative transportation options to travel from your home to work. Or even think of more complex socio-technical systems, which require additional infrastructure, material and energy inputs. What is the function of the systems under assessment? How many times will this function be performed and for how long? Where were the resources extracted to get the system to perform such functions? In order to answer such questions, we need to take a life cycle approach and consider and assess the complex system of related trade-offs along the life cycle. The term life cycle refers to the consecutive and interlinked stages of a product or service system, from raw material acquisition or generation from natural resources up to the stage of final disposal and end of life. LCA then is a quantitative methodological framework that allows linking the life cycle of a system to a spectrum of potential environmental impacts. LCA studies assess environmental impacts across an intricate network of input and output relationships. Exchanges with the natural environment also are counted. We assess these relationships and exchanges from the moment of design and development of the system through the extraction of raw materials and their processing. Then we further consider the additional manufacturing steps and operations that are required to assemble the various components of the system. We also include the distribution network and the use phase, thus the way in which potential users will interact with the system. Finally, we consider also options for the end of life of the system under assessment, together with their related environmental impacts. Let's consider the generic example of a manufacturing unit delivering a product as an output. This could be, for instance, a plant in Italy manufacturing a car. We call this a unit process in LCA. For the manufacturing unit to deliver a product, it will need a number of inputs, some of which will come from the natural environment, like water from a local river or wood from a local forest. The inputs could also be bought from service providers. In the case of a car, other manufacturing units will provide intermediate components. Energy will also be needed, likely purchased from the grid, and so on, until we identify all the inputs needed to obtain the output. All of the inputs will be linked to potential emissions. Some of these emissions will happen locally, like fumes from the chimneys of the factory in the figure. Some others will determine emissions and impacts somewhere else in the globe. What if the wood inputs I mentioned before do not come from the local forest, but from another place in the world, for instance? In LCA models, we try as much as possible to map out all of the emissions and their potential impacts across the full life cycle. Standard approaches guide the process of LCA modeling, thus allowing as much as possible for comparable studies.